Hey everyone, welcome back to Calculus 1. This will be lecture 4 of the course, and in this section we're going to discuss the topic of continuity. What does continuity mean in the context of functions? So let's go ahead and jump into it. And this will be a two-part lecture, so this will be part A of the 1.4 continuity section. So let's just go ahead and kind of talk through some nice clean examples of continuity and discontinuity. So when we say that a function is continuous at a point x equals c, the sort of everyday interpretation of that is that the function has no interruption, is smooth, uninterrupted is kind of the main metaphor you should keep in mind. There's no interruptions, there's no breaks, there's no discontinuity. Right, and that intuition of the word continuity carries through into the mathematics. So here are three examples of functions that are not continuous. So in the first case, f of c, we've got a normal function here, but the function is not defined at the value of c. Right, so you can see clearly the function has a hole at the value of x equals c. So if I were to try to plug x equals c into this function f, I would have a problem, maybe a domain problem most likely, right? So that's one example of a discontinuity, a place where you don't have continuity. Another example would be something like what you see in the middle here, right? And so here the limit as x approaches c of the function does not exist. Now, the function is technically defined everywhere, right? There's no issue at c. C has kind of this weird thing happening, but technically the function is defined across this whole space, right? But what we see when we look at the actual graph is that the function kind of moves up and then it just jumps down for some reason. You know, and a lot of functions will do this. It just has this kind of break right here, right? And so in this case, this function would be considered to have a discontinuity, even though it technically is defined everywhere. And you can see this discontinuity through this the fact that the function doesn't have a limit at c, right? And then a third option here, a third case, would be what we see over here. Now, in this case, the function is defined everywhere, and the limit exists everywhere. But when we look at the graph, when we look at the function, we see that the limit of the function as we approach c is not equal to the value of the function at c, right? So the value of the function at c is up here. The limit is down here. They're not equal, right? And so we can kind of summarize that by saying that the limit as x approaches c of f of x is not equal to f of c. Right? So in each of these three cases, we have a hole, we have a strange gap, and we have another hole, right? Here, f is not defined at c. Here, f is defined at c, but the limit doesn't exist. And here, f is defined at c, but the limit is not equal to the function's value at c, right? So these are kind of the three conditions that can come along and cause a function to not be continuous, right? So really there are, as I just said, there are three conditions for which the graph of f is not continuous at x equals c, right? And each of these three are illustrated above. And so the first one, f is not defined at x equals c, right? And so just like here, we see the function is very nice and normal, except at c there's a hole. F is not defined at c. The second condition is when the limit of the function does not exist at c, right? So the function may be defined, but it just does something weird. There's some kind of a strange break which makes the limit look weird, right? And so the limit does not exist at x equals c. And the third case is where the limit of f exists, but it is not equal to the value of the function, right? And so the limit of f exists at x equals c, but the value of the function is somehow different, right? And that can happen in this case with like a step function, for example, or a piecewise function, where the function is mostly defined here, but then at x equals c, it just has this strange value. Okay, so if any of these three things occur, then the function is said to not be continuous at x equals c. Okay, and so that leads us to a definition, right? So we can define continuity. So a function f is continuous at c if the following three conditions are met, right? So kind of take the reverse of those three. So the first thing that must be true is that the function has to be defined at c. If a function isn't defined at c, it can't be continuous at c. Okay, so the function has to be defined. Second, the limit as x approaches c of the function must exist. Okay, and then finally, that limit must be equal to the value of the function when we evaluate it at c. Right, so the limit as x approaches c of f of x should be equal to f of c. Okay, and so all of those examples that we saw previously where, hey, we're trying to figure out the limit of this thing, all we have to really do is plug in c. That was possible because the function is continuous at c, right? When you have an issue with c, with the function, and the function isn't continuous, the limit may still exist, but you can't just simply evaluate the function to find the limit. Okay, and so that's what we mean when we say that a function is continuous. All right, and so what the next couple definitions do is just extend that definition to some sort of auxiliary or ancillary concepts, right? And so the first one, we say a function is continuous on an open interval, right? So previous definition was about a point, one particular point. Now we're saying a function is continuous on an interval if it is continuous at every point in the interval. Straightforward, right? If every point in the interval we have continuity, then we say the function is continuous on the interval. Okay. Now, what happens when we don't have continuity? Right? What happens at these, what do we call these points where the function isn't continuous? And so that's the next definition. If a function f is defined on an open interval I, except possibly at c, and f is not continuous at c, then f is said to have a discontinuity at c, right? And so I've used that term already. That's what that means. Anywhere where a function isn't continuous, we say that those are discontinuities. And so just kind of jumping back up to our pictures, we would see that in each of these cases, c represents a discontinuity. Okay. Now you may be able to look at these pictures and see that these are kind of different things, right? So this one and this one maybe kind of go in a group. They're like just one hole, right? There's just like a hole there. Here, there's a gap, right? So we've got holes and we've got gaps, right? And so that's really the key to the next piece here. Discontinuities can come in two types, right? Two different types, basically the hole and the gap, right? And so the hole, we use the term removable for. A removable discontinuity looks like this, where you have a function and you just have some kind of a hole, like an issue with the domain in particular. That's usually the case, right? So removable. A discontinuity at C is called removable if f can be made continuous by merely redefining, or if the case may be, defining f at C, right? So a discontinuity is called removable if f can be made continuous by an appropriate redefinition of f at C. That's the case for holes, right? So if I just create a piece function instead here and say the function is equal to whatever at C, then I've got a continuous function. Contrast that with the idea of a non-removable discontinuity. A non-removable discontinuity is any discontinuity that is not removable. Okay. Now, what does that look like in practice? Well, for example, consider the function f of x equals 1 over x. Right? This is asymptotic, right? The function heads to positive infinity as we approach from the right. It goes to negative infinity as we approach from the left. In order to correct this discontinuity, we would have to deal somehow with this entire range, which is obviously not going to happen by changing a single point, right? right? So in this case, f is continuous at all x that are real numbers, except at x equals 0. At x equals 0, we have a non-removable discontinuity, right? And so this discontinuity cannot be fixed by the simple redefinition of a point, right? And this is one example where you have like this giant asymptote here right in the middle of the domain. Another example would be like up here, right? In order to make this function continuous, I would have to redefine a whole bunch of points, wouldn't I? I'd have to somehow connect this, right? Right now I've just got this gap. I'd have to redefine a whole bunch of points in order to bring this together and make it continuous. And so that's a non-removable discontinuity. Removable means I can adjust one point and I've got continuity. Non-removable means I have to adjust more than one point to make the function continuous, right? And so that can obviously occur because of an asymptote, but it can also just occur when you have a gap like this in the function. Okay, very good. Let's take a look at an example. Let's consider the function g of x equals x squared minus 1 over x minus 1. The domain of g is all real numbers except for x minus 1, right? We've got this hole here. Now, so this function would technically not be continuous on the real number line. It would not be continuous because specifically we have an issue at x equals 1. But notice that the discontinuity at x equals 1 is removable if we simply redefine g there, right? So instead of calling g this function, we can create a piece function that adjusts the function at the value of x equals 1. So instead of this, we can use something like this. We can say that g of x is equal to x squared minus 1 over x minus 1 whenever x is not equal to 1. And we can set g of x equal to 2 when x is equal to 1. Right? And so notice that removes the discontinuity. The function goes from having a hole here to being a nice, smooth, normal function. Okay? All right, and so that's the idea of continuity in a nutshell, right? And so there's a lot of elaboration that we can get into with continuity, and if as you continue in the class and later in Calc 2, Calc 3, and if you get into real analysis, continuity is a major topic. So just the idea of smooth, like the idea of functions without gaps and functions with gaps is there's a lot of subtle complexity there. But just in a nutshell, basically a function is continuous if it doesn't have any holes or gaps, okay? All right, we want to shift slightly to the idea of one-sided limits. So up until this point, we haven't really discussed this much, except a few references to it loosely, but let's go ahead and talk about it in a little more detail. So far we've discussed limits overall. Let's next look at one-sided limits, right? And I've kind of tried to summarize this, some of the notation here in this table. So if we approach C from the right side only, we call it a right-hand limit, right? So the idea would be here's your x and y axis, here's some value C on the x-axis, and when we talk about a limit, we normally mean let's approach the limit from both sides. But in some cases, we just want to approach the limit from one side or the other and not both. And so if we approach C from just the right-hand side, just from the positive side, moving to the left, then we can denote that using this notation here. We say that the limit is x approaches C from the right. We use this little plus symbol of f of x is equal to L, right? And so this is called a right-hand limit. Similarly, if we approach C from the left side only, we call it a left-hand limit, right? And that's just the reverse situation where you're approaching C from the left, from the negative side. And in those cases, we denote it using this. Limit as x approaches C from the left. And notice just a negative symbol. Instead of putting left and right, we opt for plus and minus. Okay? And so this is the special notation for right and left-hand limits. i.e. one-sided limits. Let's take a look at an example. Let's try to find the limit of f of x equal to the square root of 4 minus x squared as x approaches -2 from the right. Right. So if you may recognize from algebra that this is the graph of a semicircle, right? And so you'll note that the domain here is -2 to +2. The problem is if we try to plug something larger in absolute value than 2, then we end up with a square root of a negative number, right? And so it's not a real valued function at that point, right? And so if we plot this function, it looks like this, right? It's a semicircle, and it's got these endpoints at -2 and +2, right? What we're interested in is the limit as x approaches -2 from the right. And that basically means we're coming at it like this, isn't it? So we're kind of moving towards -2 from the right-hand side, which means the function's going to come down like this. And we can plainly see that if I plug in a -2 here, right, I'm going to get 4 minus 4, so I get the square root of 0, and so that right-hand limit is equal to 0. Okay, and so these left and right-hand limits can be very useful in evaluating the endpoints of domains. Okay, very good. Here's another example. Consider the function f of x equals the floor function of x as x approaches 0 from the left and from the right. Now this function here you may or may not have seen before. It's denoted with there are different ways to denote it. One way to denote it is by using these kind of emphasized or heavy braces or kind of brackets on the value of x. And what it basically means is if I plug a real number into this, I get an integer. And specifically, I get the integer that you would get by rounding the real number down to the nearest integer. Right? So if I were to plug in, let's say 2.1, then I would get 2. Right? If I plug in let's say I plug in 3.67, then I would get 3, right? It always rounds down. It floors. It's kind of the floor. That's why they call it the floor function, because it rounds down. And we can plot this. I didn't plot all of this. I mean, I didn't plot a lot of it, but I plotted some just so you can get a sense for what this looks like. Now notice here, if I plug in like 2.5, it rounds down to 2. If I plug in 3.5, it rounds down to 3, right? And so this is what the plot looks like. It kind of has this step function look. And in each case, the left side of the step is defined, whereas the right side of the step is undefined, right? And that's because of the rounding down idea. So if I want to approach, if I want x to approach 0 from the left and from the right, what does this look like? Well, if I approach from the left, then I'm on this guy here, right? And as I approach from the left, as I approach 0 from the left, the value of the function looks like it's heading towards -1. And so the limit from the left-hand side is -1. Conversely, if I approach from the right, the value of the function is on this line here, and I can see that the limit from the right-hand side is 0. Okay, and so I don't have an overall limit at 0 because the left and right-hand sides don't agree, but I do have left-hand and right-hand limits. That makes sense. Okay, and so that's another example where left and right-hand limits are very useful, and we can do limiting process related things on endpoints of intervals specifically. Okay. All right, very good. So that'll end part A of this lecture, and we'll have a second part, part B, in a moment. So just go ahead and jump to that next video. Take care.